All right. So hopefully the view counts go up because I'm seeing not a ton of people in the Zoom, and I'm going to start worrying about you guys because I know this stuff is tough, and if you're trying to cram and learn it all at the last second, it's not going to be good. All right. So where we left off was talking about kind of, okay, we can build confidence intervals for a sample mean. Well, the sample proportion is really just a unique case of the sample mean where we're looking at the mean of a 1, 0 variable. Right? So we kind of walked through and ended class with, I can actually, find the confidence interval for a sample proportion, or using a sample proportion for where the true population proportion is as well. My margin of error looks a little bit different because now instead of a population variance, well, we know the variance of a proportion is p times 1 minus p. And we don't have that true population proportion, so we just use our best estimate, which is to use our sample proportion there. But it's really the same as the sample mean. So let me switch over, start using the dot cam here. Actually, in the last section, because I just really want to, I want to highlight. Before what we were doing, and kind of you can ignore this, was take my sample mean, add and subtract, adding is the upper bound, subtracting is the lower bound. The z-score that gives me alpha over 2 in each tail times the standard deviation of my sample means, which we had this equation for. Well, the sample proportion confidence interval is the same thing. I'm just using a different statistic now. I'm building it around my sample proportion. I find the z-value the same way, and now I'm multiplying by that standard deviation of my sample proportion, which is going to look a little bit different than what we were doing for the mean, right? But otherwise, it's pretty much the same steps. We look up the z-score the same way. It's really the same kind of format. So we can actually work through a problem. Switching the screen here in class might take a second. It's taking more than 1 second. All right, there we go. So there's this old survey in 2012 that was asking people about Obamacare or whether or not they were in favor of companies covering pre-existing conditions, right? So 63 out of the 81 people said they were in favor of it. And I want to build a 99% confidence interval for what the true population proportion of people who were in favor of covering these pre-existing conditions was. Okay. So if we want a 99% confidence interval, our alpha is going to be, right, the area outside that interval, so 1%. But in decimal form, so 0.01 should be our alpha. We've got 63 out of 81. So how can I find my sample proportion here? So my sample proportion is just going to be, well, if there's 63 people in favor of it out of 81, that's a proportion of approximately 0.778. Or I think in the slides I might have this written as this kind of 7/9. It simplifies to 7/9. My sample size is 81, and we said for the 99% confidence level, my alpha would be 0.01. Well, if I think about that equation I had for my confidence interval, right, I can just start plugging some of these values in. But one thing I'm also going to need is that z-score such that the area within, right, is going to be 0.99, or the area in my tails is going to have a total of alpha in those tails, right? So if alpha is 0.01, there's half of alpha in each tail, 0.01 over 2, there's going to be 0.005 kind of in each of my tails there, half of alpha in each of the tails. Okay. So what z-score gives me 0.005 in that lower left tail? Right. So I go to my z-tables, standard normal distribution tables. I know the area in the tail that I want was 0.005. Okay. So I start looking 0.003, 0.004. Looks like I'm in between these two values, right? So negative 2.57 and negative 2.58. So I always use the higher and of absolute value of the two, so negative 2.58. And I can think about kind of positive 2.58 over here on the right-hand side. Okay. So at this point, right, now it's just going to be, plugging things into our equation. So the way I'm going to set this up first is I'm going to also find the standard deviation of my sample proportions, right, kind of that intermediate step. So that was just going to be my sample proportion, which was what, about 0.778. So 0.778 times 1 minus that, divided by my sample size, which was 81. Okay. So I'm just going to plug those in, right? And I can compute that pretty easily. Can't remember what this is off the top of my head. I think it's I don't remember, so we'll have to wait till we go to the slides because I'm not gonna try to guess. So we'll find this value, right? And now it's just a matter of plugging everything in, right? So if I think about that confidence interval equation, well, once I compute this, right, plug that value in, my sample proportion, which was 0.778, can plug that value in. And then the z-score we looked up. Now this is where, remember, when we looked up the z-score, we found negative 2.58. The positive and negative signs here are kind of built into our confidence interval equations. So really we're just thinking about, what's the absolute value. So I'll plug in 2.58. And now it's pretty basic computation in our calculators. Okay. Any questions over any steps that we did there? Okay. So we identified everything we needed. We found the z-score. We could calculate that intermediate value. So it ends up being 0.046. So this is where I was writing down 0.778. You could have also kind of used 7/9, right? 7/9 is what that worked out to be. That's 63 over 81. And then it's just a matter of plugging everything into our confidence interval equation. We add the margin of error to get the upper bound. We subtract to get the lower bound. Okay. So with 99% confidence, I could say the true proportion of people who are going to, be in favor of this policy was between about 66 and 90%, right? So that's pretty good. I mean, like if at least at the very lowest, the true population proportion is that 2/3 of people are in favor of this, it seems like something that's probably, going to go over pretty well. Okay. Any questions over this before we keep moving? All right, so let's work through another example. So let's say prior to the 2016 election that I had some information on this 912-person survey, and 46% of the people said that they were going to vote for Clinton. So before the first example, I calculated my sample proportion by the number, this many out of this many. Sometimes I'll be given information like this, where if it's 46% of people say they're going to vote for Clinton, that's a sample proportion of, right, just 0.46. Right? My sample size was 912. And if I wanted 90% confidence interval, my alpha would be, well, there's 10% outside the interval in decimal form, just 0.1. Okay. So nothing looks wildly out of the norm here. Everything looks like 0.46 would be exactly in the middle of all these, so I can't rule anything out. So from here, it's just a matter of kind of working through this problem. So first step we usually do is calculate, or I shouldn't say calculate, determine what z-score would give me alpha over 2 in each of my tails. So alpha over 2, 0.1 over 2 is 0.05. So what z-score is going to give me 0.05 in that tail? Well, I'll go back to my table. Now I want 0.05 in that tail, and what z-score corresponds to that. So I keep going. So 0.05 is in between these two. So negative 1.6, 4 and negative 1.65. So I'll take the higher of the two, 1.65. Whoops. There we go. So negative 1.65 and 1.65. So I need to go 1.65 standard deviations away from that sample proportion I saw to build my upper and lower bound. What is the standard deviation though? Well, I haven't calculated that yet, but I know it's just the square root of. Here as a reminder, we'll have it over here on the side. My sample proportion, so 0.46, times 1 minus my sample proportion, divided by my sample size. Okay. And I think this is like 0.016 something. Okay. Now that I have everything that I need, right, I've got my sample proportion, my z-score, and my standard deviation. Now it's just a matter of plugging those things in, right? So I'll take my sample proportion, I'll add to get my upper bound, that z-score of 1.65, times that standard deviation of my sample proportions, and then do the same thing, but subtract my margin of error to get my lower bound. Okay. Any questions on that? It's not too bad. So I go through, so yeah, 0.0165, I plug everything in and I get this confidence interval. Okay. So lower bound of 0.43, upper bound of 0.49-ish. Right? So how useful are these confidence intervals? We can start to do some pretty interesting things with them. So before I go on to the next topic, I did want to point out, I have some slides here with like the benchmark values a couple times. I kind of put it in between the examples because instead of using the table every single time, we're going to notice that anytime I want to find the area of alpha over 2 is 0.05. So anytime I want 0.05 in the tail, I'm always going to find negative 1.65 and 1.65. Anytime I look up 0.025 in the table, I'm going to find 1.96. So these are going to be some benchmark values that we start to see pop up quite a bit. Okay. Okay. So we've got this lower and upper bound. The next thing that I want to kind of proceed to as well. What if I had the same survey that 40% of people were going to plan to vote for Trump? Okay. So what changes there? Well, I have the same sample size, right? That sample proportion is a little bit different, so it changes the standard deviation of my sample proportions a little bit. But if I want to go build a 90% confidence interval, that's exactly what, here we go, right there. It's exactly what I did before for Clinton. So when I look up the 90% confidence interval, there we go. My alpha is still going to be 0.1. Alpha over 2 is still going to be 0.05, right? When I look that up, I'm going to find the same z-score as before. So really the only thing that changed was my sample proportion. It's the only thing that changed in that equation. So I could very easily, right, find the lower and upper bound for Trump in the same way. So here's where confidence intervals get pretty useful. So I'll eventually switch off this, but I need this for the numbers. If I'm just plotting this out, and I'm just going to do it to the second. Well, I'll keep this one out to the decimals, right? So the true population portion of people who are going to vote for Trump could be anywhere in this range of values, right? If we then go back, the population portion of people who are going to vote for Clinton, 0.4328 and 0.4872. Okay. So first of all, notice these intervals aren't super wide, right? I mean, the widest confidence interval for a proportion you could ever see is, it could go from 0 to 1. So the widest we could ever see is 1. So here we've got about a 0.05 kind of in width confidence interval, so pretty narrow. The reasoning why? Well, when we have a really high sample size, that's going to, right, large denominator. It's going to drive down that standard deviation of our sample proportions. So it allowed us to kind of get a pretty good kind of narrow confidence interval. But now that we have this, kind of plotted the values, what we could say is, well, look, with 90% confidence, I mean, the true proportion of people who are going to vote for Clinton is somewhere in this range, even if it was the lowest, the lower bound value, right, the lowest it could be, and even if the population proportion of people going to vote for Trump was the upper bound, the highest value it could be at 90% confidence, I could say here that, well, with 90% confidence, the proportion of people who are going to vote for Clinton is greater than that who are going to vote for Trump. So if there's no overlap in the confidence intervals, then you could say that, you know, this person is going to receive fewer votes than this person. Right? Now, what happens though, right? So if there's no overlap, right, we can make some interesting statements, right? Because we know that 90% confidence, one of these has to be the true population proportions for Clinton. One of these has to be the true for Trump. Wherever they're at in that range, the proportion for Clinton will always be greater than that for Trump. Right? So we could have predicted the election based off this poll prior to the election occurring. Right? Now, well, what if we wanted to say this with 99% confidence? What's going to happen there? Well, let's think about our equations. Okay? Well, actually, where do we have this? Oh, I'll use this guy here that we had earlier instead of redrawing it. So when I wanted 90% confidence, here were my z-scores, right? So if I wanted 99% confidence, my alpha becomes 0.01. When I divide alpha by 2, I'd have 0.005. So I'm going to need if I want 0.005 in the tail, I'm going to have to go a further number of standard deviations out. So I'm going to need a larger z-value. If my z-value goes up, what's going to happen? Well, if my z-value goes up, my margin of error gets larger, and I'm going to have a wider confidence interval. So if I wanted to say this with 99% confidence, based off of how close these two values are, right? This is just barely below the upper bound. The upper bound for Trump is just barely below the lower bound for Clinton. It's likely that if I wanted a 99% confidence interval, and I'm probably exaggerating this a little bit, but right, they're going to get wider, okay? And now all bets are off, right? I can't really make any statements at the 99% level because the proportion of people who are going to vote for Trump could be here. The proportion of people who are going to vote for Clinton could be here, in which case Trump is higher. But it could be that the population proportion of people who are going to vote for Clinton is up here. Trump could be all the way down here, right? But as long as there's overlap, I can't really say with 99% confidence which of these candidates is going to receive a higher number of votes, okay? So when confidence intervals don't overlap, we can say things at that level of confidence, right? That one group is going to be greater than the other, one person has a proportion greater than the other. If they do overlap, I can't say anything, right? At least not with that level of confidence. Any questions on that before we keep moving? Nope. Okay. All right. So I've got a bunch of other, so that was kind of the main one. I've got some other slides in here. I'm not going to really spend much time on them. I thought it would be cool to kind of do both presidential elections. I was hoping something good came out of it. This one was interesting because they were so close, and it really highlights that, you know, overlapping, non-overlapping issue. It also, I pulled this one from Fox News, so I thought it would be like the most biased one that I could find. And so I did find there, well, we really couldn't quite predict the election at the 99% level, but we could at the 90%. The problem with looking at some of the data from the last election with Biden and Trump, notice the lower bound for Biden here was very far above the upper bound for Trump. So even if you go out to the 99% level, these don't overlap. Which, sure enough, I mean, this is what ended up playing out, right? The true population proportion was higher for both Biden and Clinton, right? So making these predictions, like we can see, we're not, you know, we're going to be correct 90% of the time. But it's just really some more examples with some slightly different numbers. you could kind of work through them by hand if you want to, try to reproduce the answers to make sure that you have kind of a good understanding of what's going on, or just to get some more practice. But I'm not going to spend time kind of covering them. But it is interesting maybe to look at some of what these polls were predicting. So I think what I did was I grabbed the poll that had the widest margin, right? And then I also grabbed one that had a really high number of people surveyed, but that was a little bit closer, right? So 51-47. And I noticed there at the 90% level, I actually do get the upper bound for Trump was just barely past the lower bound. I was really, really stretched and trying to look for a survey that had it where these overlap, and there really was only this one. All the other ones looked more similar to this, where they were pretty far away and not overlapping. But you could do whatever race you're trying to predict. You could do this thing where you build these confidence intervals. In fact, a lot of the times what they'll report to you is they'll say something like 51% of people are going to vote for Biden based off this survey, with a margin of error of 2%. So really what they're telling you, they did the work, they found the Z-score, they know calculate the standard deviation of the sample proportion, and they're just going to report to you what that margin of error is. So a lot of times when you see these prior elections, you see these predictions or you see these polling numbers, the margin of error that they're telling you, you could really use it and just add it and subtract it to that sample proportion and build your own confidence interval based off of what they're reporting to you. Okay. All right. So, I didn't want to do that. I wanted to escape. We're going to go back to, and I had the other sections open. So let's look at, I think I still saved it in here. Yeah. That confidence interval examples that file that we were working with last class, right, where we had kind of the undergraduate enrollment data. Right? I'm going to show you how we could build these confidence intervals for sample proportions as well. So first of all, I'm just going to delete this because I'm going to rebuild it for you, just as giving you more, just kind of another look at it. So we did that with sample means last class. So let's have this variable, which is a 1 if the total undergraduates is greater than 10,000, and then a 0 when it's not. Okay. So I have this 1, 0, this binary variable. If I wanted the proportion, I have mean proportion here, but I can think about, I really just want to calculate my sample proportion of schools that have more than 10,000 students, right, or 10,000 undergraduates. So if I find the mean of a 1, 0 variable, the numerator is just going to add up all these values. So it's going to take 1 plus 1 plus 1 plus 0. Well, the zeros don't impact it at all. So basically the numerator is going to be the number of schools with more than 10,000 undergraduates, and then it's going to divide it by the total number of observations. Well, that's a sample proportion, this many out of this many. So if you use that average function in Excel to calculate the mean of a 1, 0 variable, that's just going to give you your sample proportion. Okay? Now I'm showing you this for a reason. Some people won't watch this and probably won't hear this, but I guarantee I'll have people turn in the next Excel assignment where they try to use the count formula, count up the number of ones and then divide it by you don't need to do that. You can simply take the mean of that 1, 0 variable, okay? You can find your sample size pretty easy. We did this last class with just using that count function, right? So my sample size, maybe kind of helps to think about this, is n, right? My sample size. So the other two things that I needed when building confidence intervals was those z values, and then also this standard deviation of my sample proportion. So one thing I'm going to do is up here just put standard deviation of my sample proportions. Now, I think that this just makes it easier. We talked about last class, like I can do it all in one cell if I really wanted to. But it's going to make it a little bit easier this way. So just a reminder, what was our equation that we had for the standard deviation of our sample proportions? So we were going to just basically use Excel to be our calculator. So we're going to take the square root, so SQRT, of the sample proportion, which we had in this cell, times 1 minus that sample proportion, and then divide by our sample size, which here was in what? Cell Q2. Okay. So I'm just using Excel to be a calculator. Now I've got that standard deviation of my sample portion. The only thing left I need is that z-score, right? So I'm going to go down here and hopefully remember what we did last class. So if I want alpha over 2 in the tail, and I want to find the z-score that corresponds to that, right? That's what we were doing here, right? We know the area that we want in that lower left tail was alpha divided by 2. What z-score would give that to us? Well, that's where we can use, we're working in reverse. We know the area in the tail, we want to find the z-score. So norm.est, right, we're dealing with z-score, standard normal distribution. And then .inv is where we know that probability, or we know that area in the tail is alpha over 2, and we want Excel to give us a z-value that would give that to us. Okay. So I hit enter here. Okay, I forgot about the issue here, which is that once I go to calculate my lower and upper bound, the negative and positive are already built in. And when I'm looking up alpha over 2, I'm looking at a small value in that lower left tail. I'm always going to get this negative z-value. So we said basically we just want to take the absolute value, ignore that negative sign, so I can use that ABS function and just put parentheses around norm.s.inv. So this will find the z-value, drop the negative sign essentially. Now I'm done, I've got it. I can copy this down so that I can get the z-values, right? It updates that cell reference to using the new alpha so that I could build the 90, the 95, and the 99% confidence levels, confidence intervals. Okay? So I'm going to be building 3 different confidence intervals here. So the first one, right, if I want to find the lower bound, well, that's just take my sample proportion. So equal sign, here's my sample proportion, minus that z-value that gives me alpha over 2 in the tail, times the standard deviation of my sample proportions. That's all it is. And especially once I've calculated that intermediate step, it's a lot easier. I'll say this with the confidence intervals. I would set it up the way that I'm doing it now, and like we did last class where I calculate the standard deviation of whatever sample statistic I'm looking at, so whether or not that's sample means or sample proportions. Because if you try to like enter this all into one cell, like I plug this equation in here and then try to type all that out, it's just a lot easier to make mistakes with my parentheses. Okay. But otherwise, this way makes it pretty easy, I think. Okay, so if I hit enter here, I'm like, oh, let's copy it down and get my lower bound. Well, that doesn't look right, right? So what's going on here? Well, it's updating my z-value, but it's also moving my reference for where the sample mean and the standard deviation of my sample proportions is. So, like, oh yeah, I gotta freeze those, right? Doesn't matter what level of confidence I'm building my confidence interval for, I'm building it around the sample mean. So I'm gonna freeze that. I should always be using the sample mean. And my standard deviation of my sample, that doesn't change based off of the alpha or based off of the confidence level I want. So I should be freezing that as well. So now when I copy this down for the 95 and the 99% confidence level, it'll still be using the sample proportion and the standard deviation of my sample proportion. It's just going to update the z-value. Because at higher levels of confidence, I need to go out a further number of standard deviations. Okay? So now when I copy it down, this looks a little bit more reasonable. Okay? For the upper bound, probably the easiest way to do this is double click on that cell where you had the lower bound. And you just want to copy this formula. I'll hit enter to get out of there. Paste it, because the upper bound is the exact same thing as the lower bound. It's just instead of subtracting the margin of error, I add it. So once I just change that, now I can copy this one down, and I'm done. Okay. So one nice thing that we can kind of see play out here is when I was going to higher levels of confidence, notice that meant, oh yeah, a smaller alpha value, so a smaller alpha over 2 in the tail. So to get a smaller value in the tail, I'd have to use a bigger z-value or a larger in absolute value z-value, which is sure enough what's happening. Well, if the z-value goes up, my margin of error goes up, and when I add and subtract that to my sample proportion, I get a wider confidence interval. And sure enough, my lower bounds are getting lower and my upper bounds are getting higher. I'm getting a wider interval when I'm going to higher levels of confidence, right? Higher levels of confidence corresponding to lower alpha values, okay? Any questions over anything that we just kind of went over here?
Yeah, I had a question.
Yep.
So, I re-downloaded the Excel sheet and it looks very different from this one. Will there be an updated one
Yep. When
loaded up?
I'm done today, I'll post this up on I was going to mention that. I'm going to post this up on Canvas and call it like confidence interval example in class work. So I'm going to leave the original one up there because when you're actually working on your the next Excel assignment, this one has a lot of extra stuff going on that I was showing you different ways, and I don't want you to be confused. Like, I can't really remember. I got to go back because I told you not to use the confidence.norm, but I showed you how it can work. So I'm leaving the original one up there because that's the one that will be the best template for the next Excel assignment. But I'll post this one after class today, and I'll then kind of use this one as the living one that I keep updating it as we work through the other worksheets. It's just going to contain a lot of stuff that you don't necessarily have to do as well.
Okay, cool. So,
Yep.
for a reference, would you recommend then that we use this one for the Excel assignment?
I'd probably use the original one I put up there. In terms of like, it's just going to be more clean, right? This one is going to have, like, obviously you don't have to build the confidence intervals twice, right? I showed you two different ways to do it. You don't necessarily have to use this if statement. So it's, which one's better? If you actually are here today, then this one, when I post it, will probably be more helpful, the one that we worked through in class, because you'll be able to remember like what everything means. Now, for people who didn't sit through this lecture or didn't watch it, probably wouldn't suggest using this one because we had a lot of extra stuff going on as well. Does that kind of make sense?
Yeah, that clarifies it. Thank
Okay.
you.
Okay. That's a good question though. All right. Any other questions before we keep going here? So I will post this after class today. I also will post the next Excel assignment. You'll be able to get about 2/3 to 3/4 of the way through it. We'll finish up on Monday of next week with the last kind of piece of the puzzle that you would need. Maybe Wednesday. I think we'll get through it on Monday, but a little of it may get pushed off on Wednesday. But I think we'll have at least talked about enough on Monday that you could actually probably go in and figure out kind of this sheet and how it matches up to the Excel assignment as well. So they'll be getting that posted after class today. It'll be due 2 weeks from today. So you got quite a while to do that. I think that should cover it. Any other questions on this? Oh, there was one thing I wanted to use this to point out. Just keep reiterating kind of the same facts. But if and let me see where the best one we have is. Where's the, oh, here, right in front of me. So notice, if I look at my sample size, if I were able to increase my sample size here, so let's say I don't have every university here, but I go out and I get a bunch more and I'm gonna, have a higher sample size, right? So 500 instead of 111. What that should do, right, is drive down the standard deviation of my sample proportions. Well, if that's driving down the standard deviation of my sample proportions, that's going to make my margin of error smaller, and I should get this more narrow confidence interval, okay? So sure enough, if I hit enter here, notice before it was what, 0.73 to 0.85? Now it's 0.76 to 0.82. And I don't remember what the standard deviation was, but I think it was 0.03 something. So the standard deviation has kind of went down, which lines up with what we've been talking about. So just kind of seeing that play out here in Excel after we had everything built up, I think is kind of helpful. And the way I remember this is always through the equations, right? Like I think of it as like, okay, if I take a higher sample, it's going to drive down that standard deviation. It's going to be a more narrow distribution for my sample proportions, which means when I'm building my confidence interval, going the same number of standard deviations away, well, the standard deviation is going to be smaller, so I get a much narrower. Right? That's how I think about it through the equations. But an intuitive way to think about that is if I have a higher sample size, I just have more information about the population. If I have more information about the population, I'm going to have a more accurate idea about what the population mean is. And what does a more accurate idea mean? A more narrow range of values. So having a higher sample size, more information about the population, I can really narrow down this confidence interval And what I'm doing when I narrow down the confidence interval is I'm narrowing down my prediction about where that population mean or that population proportion actually is. Okay. All right. So, So one thing that's a little bit goofy, I was going to use the other slides to show this to you. So if we go back, remember, back a little bit further, I said that really the standard deviation of my sample proportions, I should be using that population proportion, right? Because I know the variance for the original the original data I sampled from should be p times 1 minus p, or that population proportion times 1 minus it. But I don't have that. That's the whole reason I'm building a confidence interval. So I had to use an estimate, which was the sample proportion. Okay? So why then, when I was looking at sample mean examples, how did I know the population variance when I didn't know the population mean? Well, I gave you some examples where maybe it was like some machinery. We knew that the variance on the production process is a certain thing, but it seems kind of unlikely. In fact, it is very unlikely, right? Usually we don't know the population variance, right? But what we can do is basically just use our sample variance as a best estimate for what it should be. So we're going to write the standard deviation of my sample means a little bit differently. The notation is going to be a little different. And it's still the standard deviation of my sample means. If I write it with an S, it indicates I'm using a sample variance instead of the population variance. Okay? So what is this going to affect, right? Well, can I just go on and do the same procedure as I was before? Kind of, but there's going to be a slight kind of wrinkle in it, okay? So before, we had something like this, right? So before, when we knew the population variance, this was the setup, right? We could plug that in. Now, we have to write it a little bit differently because we're calculating that standard deviation of our sample means, but we're using a sample variance to estimate that population variance. Now, because I'm using a sample variance here, to explain this in the most intuitive way and not get lost in kind of some type of a mathematical proof, when I'm calculating, my sample variance, I'm dividing by n minus 1 here, right? Like going back to like early in this course. What the problem that is going to do is, well, if I'm using this as my estimate for the true population proportion, population variances or standard deviation, well, if I have a small sample size, like 2, then I would be dividing by 1 instead of 2. That's going to cause a huge difference. If I have a large sample size, I'd be dividing by 99 instead of 100. That's not going to make as much of a difference. I'm not going to be as far off. So because we're using this sample variance that's using this n minus 1, when I try to convert values into z-scores using this sample standard deviation of my sample means, you could say, it's not going to quite be a standard normal distribution. In fact, it's going to be a student t distribution, but we're still going to be looking for a t value instead of a z value that gives us alpha over 2 on each side of our confidence interval. So the procedure is still the same. It's just that we're going to have to use a different distribution. Because when I create z-scores, where I was trying to create z-scores with using the standard deviation of my sample means with a sample variance, they aren't z-scores. They actually come from a distribution that's not standard normally distributed. So it's not a mean 0 variance of 1. It's still a normal distribution. The t distributions are still normal. They have a mean of 0. The only difference is they're going to have a variance, because we're dividing by n minus 1, that is larger than 1. And how much larger than 1 is that variance will depend on what my sample size is. This idea that when I have a small sample size, dividing by 3 instead of 4 is going to create a much larger difference than if I divide by 99 instead of 100. So the student t distribution, right, is actually not just one distribution, but a bunch of them, right? At every single degrees of freedom, I have a different student t distribution. They all have a mean of 0, but the variance is a little bit higher than that standard normal distribution, so the variance is higher than 1, right? So we're going to use this thing called degrees of freedom to identify which of these student t distributions that we should be using. The degrees of freedom will be n minus 1. So if I look at my sample size, right, all I do is subtract 1. That gives me my degrees of freedom, and I can identify what student t distribution I need to be using. Okay. So some of the properties we already talked about, right? I said it has a mean of 0, but it's also symmetric. It's normally distributed. So it's still symmetric around that mean of 0, so very similar to the standard normal distribution. It's just more spread out. The variance and standard deviation are greater than 1. However, as my degrees of freedom gets larger and larger, eventually it starts to look more similar to a standard normal distribution. So if I could get an infinite degrees of freedom, my student t distributions actually become the standard normal, right? And really anything over 100, any degrees of freedom over 100, the student t and the standard normal are approximately the same thing, right? They're still a little bit different, but almost the same thing, okay? So before we kind of go too far into it, I think I'll leave this. I'm going to put this up on Canvas, but this is we're going to start using this table, which is the student t table. Okay, I don't think it's currently up there. I guess I could check. Can't remember if I dumped it in here, but oh yeah, I did. I guess I did put it up there. So the student t table is already up there, and it works a little bit different than the standard normal table. So first of all, it's looking at the area in the upper right tail. So we're only going to be thinking about positive t values, but it's symmetric. So I really could like reproduce this same table, but just make everything negative and think about the the left side of the distribution. But here it displays things as the right tail, upper right tail. And now our column headings become the area that we want in that tail. So it's kind of like the reverse of the standard normal table. The standard normal table, we had the z values as the row and column headings, and my area in the tail was in the middle of the table. With a student t table, the area in the tail is my column heading, and then these t values that give me this area in the tail are the values in the middle here. I then have my degrees of freedom, right, over here as my row headings. Row headings. So let's say I had a sample size of 30. So my degrees of freedom would be 29. These are the values that give me different areas in that upper right tail. So let's say I had an example where, since we did it today, alpha was 0.01. We divide it by 2, so the area in each tail would be 0.005. So I look up that area in the tail of 0.005 all the way down to that degrees of freedom of 29. And the t value that gives me 0.005 in that upper right tail is 2.756. So this would be the value that I would then plug into my confidence interval equation. Okay? So I just want to kind of briefly show you how we use that student t table before we end today. It works a little bit different than that standard normal. And you can kind of see already the limitations, right? I only have 6 areas in the tail I can look up. So we'll talk about these limitations more once we get to hypothesis testing and look at how we can use this distribution in Excel. But the biggest problem is not going to be with confidence intervals. When it comes to confidence intervals, we have a lot of our benchmark values that we want in the tail here. So we can use the student t table to find those t values when we're building confidence intervals. And the fact that we're limited to kind of these areas in the tail shouldn't be a big problem, because we typically only build confidence intervals at the 90, 95, and 99% levels anyways. So if we divide those by 2, that would be 0.05, 0.025, and 0.005. So those areas in the tail to build confidence intervals are on this table and won't really present any problems that we don't see every single area in that upper right tail, right? I mean, really, this table was built by someone integrating that function, right? There's a probability density function associated with the student t distribution as well, right? It's a normal distribution, so it has that same probability density function. So it's really just a matter of doing that integration, finding the area under the curve. But here, this table only presents 6 different areas, okay? All right, so we'll start using that student t table a lot in class. It's just under the main files page. I'll get the next Excel assignment put up there when I get back to my office today. And other than that, the Connect homework is due by the end of the day today. So if you have any last minute questions, I'll try to kind of get some quick email responses out this afternoon if you send those to me. Otherwise, have a good weekend, and I will see you guys on Monday.